Good morning. Welcome you all to the Radiation Oncology Physics course, and today we are going to deliver the lecture number 11, and in this lecture we are going to discuss the various type of medical radiation generators used in radiation oncology department. So there are various type of equipment we are using in our radiation oncology department or hospital service to treat the cancer patients, and we have divided these medical radiation generators. We are going to discuss elaborately because this is very important topic, and we have divided these medical radiation generators in 5 lectures, and in the first lecture we are going to discuss the imaging and simulation equipment which are used in in a radiation oncology department. So learning objectives, we will first discuss what are the types of radiation generators and what are the types of equipments we are using, and first imaging equipment we will discuss about little bit X-ray, CT scan, ultrasound, MRI, and we will discuss various radiotherapy simulator. They are X-ray simulator and CT simulator. Now this is a very important slide where we are going to discuss various kind of equipment which are used for patient treatment purpose or patient management purpose in the radiation oncology, any radiation oncology department. So first is we need to diagnose the patient by imaging various imaging devices, imaging equipments. They are based on X-ray, they are based on CT scan, they are ultrasound, ultrasonic device, they are medical resonance imaging device, MRI, they may be SPECT, single photon emission computed tomography. The imaging equipment may be PET, positron emission tomography unit. So these are imaging equipment which we are normally used in our radiation oncology department. First is X-ray, CT, ultrasound, MRI, SPECT, PET, and we also use various type of simulation device. This simulation device, we simulate the patient treatment in all these simulation device. Without treating the patient, we can simulate, we can plan the patient, and according to this simulation information we can treat the patient, because each and every patients, they are different in their size, their shape, their anatomic body informations, and there may be different kind of cancer sites and their size, and all these informations we collect from the simulation and imaging equipments. Now to give the totality of this slide, we use various kind of therapy equipment. We treat our patients by radiation. One is teletherapy and another is brachytherapy, and this teletherapy means far, tele means far. So we treat the radiation patients from away from the patient body. The source is located away a distance from the patient's body. But in brachytherapy, we treat the patients by close proximity within the target volume, or sometimes we apply some applicators, or sometimes we directly insert the radioactive isotopes to the target volumes of the patients, which volume is needed to be treatment. And in teletherapy, there are various kinds of equipments used. First type of equipment, teletherapy equipment, is radioisotope based. They are cobalt 60, and some equipments, teletherapy equipments, are X-ray based, and they may be kV range, means kilo voltage range, where the equipments are Grange ray therapy, contact therapy, superficial therapy, ortho voltage therapy, and super voltage therapy. And in mega voltage range, we use the LINAC, that is linear accelerator, where we accelerate the electron and hit the accelerated beam of electron to a target, and we get the X-ray, and sometime we use the electron also. This is also coming from the linear accelerator. We also use betatrons, and we also use particle therapy for particle therapy for the cancer patients, where we use the cyclotron. In brachytherapy, we use low dose rate, medium dose rate, high dose rate and pulse dose rate type of brachytherapy unit. While we treat the patients, as I have already said, that there is we are using our we treat our patients with sub-millimeter accuracy, and this sub-millimeter accuracy needs to be verified during their treatment. So we have various kinds of verification equipments. These verification equipment are based on X-ray based, simply X-ray imaging of the patient target, and their portals are demarcated portals are matching or not. We can verify. We can verify by CBCT. They are actually cone beam CT scan, and we may have MB-CBCT and KB-CBCT, MB-CBCT and KB-CBCT. This is MB-CBCT and KB-CBCT. We also nowadays there is some advanced equipment which are using MRI scanning for verification purpose. So radiation oncology department having the equipment of imaging equipment, we have simulation equipment, we have therapy equipment, we have verification equipment. Where in imaging equipment we use X-ray, CT, ultrasound, MRI, SPECT and PET, but these two ultrasound and MRI, they have added advantages. They are not involving any type of ionizing radiation, which is very useful, that they are not using ionizing radiations. As we know that ionizing radiations are hazardous to the human body. And in simulation equipment, X-ray simulation, CT simulation or PET CT simulations. In therapy equipment, we use cobalt based teletherapy, we use X-ray based teletherapy, and they are KV range or MV range. KV range are Grange ray, contact, superficial, ortho voltage and super voltage therapy, and in mega voltage range we use the LINAC. We also use sometimes electron beam therapy. They are also produced from linear accelerator. We use betatron, we use particle therapy, and they are coming from the cyclotron. In brachytherapy, means short distance therapy, we treat the target volume in very close proximity or within the target volume. We can insert the radioisotopes. They are basically dose rate. They are dose rate according to the dose rate. There are various equipment, and first is LDR, MDR, HDR and pulse dose rate, that is pulse dose rate. Now imaging equipment. X-rays were discovered by Ranjan. We all know that 1895, and while studying the cathode ray in a gas discharge tube, he observed another type of radiation was produced. A different kind of radiation was produced, and this radiation is detectable outside the glass tube, and this another type of radiation is also can penetrate the opaque substances. It can produce fluorescence. This radiation blacken the photographic plate, and this unknown radiation he named as X-rays, as we define any unknown as X. Now this is we know this is the physics of behind the X-ray generations. We know that charged particle may interact with the electrons, and because by the excitations they can excite the electron or they can ionize the atom. But when the charged particle interacts with the nucleus, there is a change of directions, or there is a breaking of radiations, means the radiation have a break, and because of this break there is a emission of photons, they are actually X-rays. They are X-rays, and these X-rays are known as Bremsstrahlung X-rays. Now here is a X-ray tube where a high voltage, there is a glass tube, this is sealed tube, and this is high pressure vacuum is created within the tube, and here is a filament circuit, and here is a anode which is connected to the high voltage supply. Now the electron beams are produced from the filament, and they, while there is a voltage supply, they travel towards they attracted towards the anode, and they accelerate, and they hit the anode, and after hitting, because of this Bremsstrahlung, these X-ray radiations are produced. So this is the theory and physics behind the X-ray production. So you should very clearly understand that the X-ray is produced because of Bremsstrahlung radiations. You also know there is one different kind of radiations that is known as characteristic X-ray, but they are not used for treatment or for diagnostic purpose, for imaging of the patient. Here this is the type of X-ray. This is one type of X-ray tube, which this is a schematic diagram or representative diagram, where this glass jar is high pressure vacuum is created within the volume, and there is a filament, and after giving the high voltage supply to the anode and the cathode or filament, the electrons is produced, and these electrons attracted towards anode, and there is a high Z materials, and this is a target, and this is high Z material, and this are after hitting of this high Z materials, because of Bremsstrahlung effect, Bremsstrahlung phenomenon, the X-ray are produced, and this X-ray is used for diagnostic radiology. Now coming to the computed imaging equipment, that is very popular imaging equipment. You all know about the computed tomography, where as we know that by X-ray we only get the two-dimensional images of the patient, but we do not have any idea of target volume, or we need some anatomic information. So internal organ volume we need information, and we also need the tissue density mapping of the patient body. What type of tissue is constructed the patient body, and in CT imaging we use a fan beam X-ray. Fan beam means there is a radiation source and it is coming like a fan. This is the fan beam geometry. If one source and coming a single ray, that is narrow beam geometry, and if it is diverged in a very fan manner, in fan like structure, then we call it as a fan beam X-ray. So in CT scan there is a X-ray tube, and it produces a fan beam, and it is rotating X-ray tube, and we have a detecting assembly. This is the detector assembly or detector panel, and after this fan beam is transmits towards the patients from this position to this positions. Again there is a fan, and if when this is the X-ray tube is here, we will also get like the fan beam transmission or detected this detector assembly, and there is this tube actually scans the patients, and it's synchronous with the detector, and there is a sufficient number of transmission measurement. We will get transmission measurements and assessment of different attenuation coefficient, because we know that bone have different type of attenuation coefficient, soft tissue have different type of attenuation coefficient, and also we know that there is various tissue having different type of attenuation coefficient. By assessing this different kind of attenuation coefficient, we get a map which gives the we can reconstruct this attenuation coefficient of various structures, and we with the different attenuation properties. We can reconstruct this attenuation in from this transmission information. We can create a map. Now, reconstruction of an CT image slice by any CT is a very cumbersome mathematical process, and it is done by computer by typical algorithm, which is actually devised by the various companies, and this reconstruction algorithm generates actually CT number. Now, what is CT number? CT number is also known as Hounsfield number. CT number H is the mu, that is linear attenuation coefficient of tissue minus linear attenuation coefficient of water divided by linear attenuation coefficient of water. So, all the linear attenuation coefficient of any kind of tissue is normalized with water. So, water is the normalized point by which any kind of tissue attenuation coefficient is plotted, and by which we can the CT image slice are reconstructed. Now, here is a CT scan. This is a circular type of machine, and by which these kind of axial sections we obtained, and this axial section further reconstructed, and they give the different planar image of the patient. They are generated by reconstruction process. They are not automatically generated. We will discuss later that these sections are known as transverse sections of the patient's transverse slice, and by stacking all these transverse sections, computer create another image plane, and we are using also this image plane for various diagnostic and various other purpose. Now, ultrasound imaging, we know that this is not involving any kind of radiation, ionizing radiation. We have included ultrasound to complete our lecture, that what kind of machines or what kind of equipments we are using. Ultrasound is a ultrasonic use, where ultrasound wave is a sound wave and having frequency of more than 20,000 Hz, and it is inaudible to our human ear. And for diagnostic radiology, for diagnostic purpose, we use 1 to 20 megahertz of frequency, ultrasound frequency, to detect any kind of, to scan the patient body. Ultrasound may be used to produce image by using the reflection of the ultrasound, or sometimes we use the transmission of ultrasound. Now, reflection mode is commonly used mode of ultrasound. Transmission modes are very rarely used, and because ultrasound penetration is very less, so transmission ultrasound is very rarely used. These reflection or echoes are created because there is a difference of acoustic impedance of different tissue interface. Now, what is acoustic impedance? Acoustic impedance is the density of the medium multiplied by the velocity of the ultrasound. So, this is the acoustic impedance Z, and this Z is different for different tissues. Now, if there is a larger difference between two types of media, suppose lung and air, or lung or soft tissue, or bone or soft tissue, so there is a large fraction of ultrasound reflection we get, and ultrasound wave generated and received by the same probe. The same probe, that is known as transducer, and this probe is generate the ultrasound and also received the ultrasound by using the piezoelectric effect. It is a physics phenomena by which this ultrasound is generated and the ultrasound signal is received. Now, one more important imaging equipment is magnetic resonance imaging. It is also not involving any kind of ionizing radiation, and the basic physics of MRI is magnetic resonance. Now, magnetic resonance is the resonance transition between nuclear spin state of nucleus with applied radio frequency, that is the resonance transitions of nuclear spin states with applied radio frequency signal and with the presence of an external magnetic field. What happened? That we know that nucleus having intrinsic spinning motions with angular momentum, and these rotating charge act as teeny magnets, and these magnets having a magnetic dipole moment. Now, what is dipole moment? Dipole moment is the property by which we can say that how quickly a magnet align itself along the external magnetic field. This is the dipole moment, and because of dipole moment, the nuclei align spin axis along the external magnetic field and as well as orbits around this magnetic field axis, and this is known as Larmor frequency. A second alternating field is generated by applying the alternating voltage to the RF coil, and which is perpendicular to the H, means external field. Now, when RF coil is turned off, the nuclei return to the original alignment, and this phase is known as relaxation, and which induce a RF signals to the RF coil, and the NMR image is formed. So, this is the MRI magnetic resonance imaging is a kind of magnetic resonance where we see a resonance transition is happened between nuclear spin state of the nucleus with the applied radio frequency in the presence of external magnetic field H. Nuclears having intrinsic spinning motions with angular momentum, and these rotating charge act as a teeny magnets, and they have a magnetic dipole moment, and dipole moment is the property of any magnet, that how quickly a magnet align itself along the external magnetic field. And because of the dipole moment, the nucleus spin axis along the external magnetic field, and as well as it orbit around this external magnetic field axis, and this is known as Larmor frequency. A second alternating field is generated, and alternating field voltage to RF coil which is perpendicular to the H. Now, when we turned off the radio frequency, the nuclei return to the original alignment. This is known as relaxation, and which induced a signal to the RF coil, and nuclear NMR signal image is formed. Now, here is the magnetic resonance imaging, and these are kind of image. You can see here all the planes are created by they are not processed or they are not reconstructed from any kind of things, but they are actually planar image directly we get from the MRI machine. Now, here is a comparison of CT versus MRI. CT, we know that it use the ionizing radiation. MRI use NMR signal. There is no use of ionizing radiation. So, MRI is less hazardous in terms of ionizing radiations. CT provides the anatomic information. This is also MRI also provide the anatomic informations, and CT provides the transverse axial image, and raised planes are displayed by reconstruction, means these other planes are actually processed image, but MRI scan directly and image all the planes. CT having better imaging, CT are better for imaging of bones, and MRI imaging are better for soft tissue imaging. They are better in soft tissue imaging. In CT machine, CT scan, we need a very less scan time, but in MRI we need higher scan time. Now, what is the importance of scan time? Because there is motion artifacts if we take long time scan time to image any patient, because of our various kinds of internal or external movements of the patient body. So, for less scan time, CT is beneficial because of its less scan time, and it is little bit inferior than the CT scanning because of higher scan time, and they MRI images may get some motion artifacts which are deform, which distort the information of the images. And we have wider range of contrast for CT scanning, but now in current days there are not much more contrast or better contrast available for MRI scanning. CT scan, there is no problems with metallic implant, because many patients they come for imaging with the metallic implant with their body, so they are not fit for MRI scanning, so they scan by only CT machines. So MRI metallic implant patients are not possible in MRI scanning. So if we compare CT and MRI imaging equipments, we can see in some cases there are some advantages of CT machines and there are some inherent advantages of MRI imaging. So CT and MRI are complementary imaging modality. They are not replacing any, they are not replacing the others. So they are complementary imaging modality. Here you can see this is the MRI image and this is the CT image, where this is the brain of MRI of brain, and you can see the brain tissues are very prominent in MRI, and bones are very prominent in CT images. Now coming to the simulation equipment, there are various kinds of simulator which are used in for our radiotherapy treatment purpose, where we simulate the treatment process in a machine which duplicates all the geometrical, mechanical and optical parameters of the therapeutic machines except the therapeutic radiation source. Means radiotherapy simulator is an apparatus which duplicates all the geometrical, mechanical and optical parameters except the therapeutic radiation source. In simulator we do not have therapeutic radiation source, we have a diagnostic radiation source, and we know we have two kind of broadly we can divided the simulator in two type. One is X-ray simulator, they are also known as radiographic simulator, or they are known as conventional simulator, where the diagnostic X-ray source is used and display the treatment portal in two-dimensional. Now in CT simulator, a CT scanner is converted to radiotherapy CT simulator, but there is difference in 2-3 points than the diagnostic CT scanner. In the CT simulator, we have a large bore which is needed to accommodate the various kind of accessory we use for treatment of cancer patients. We need a flat tabletop, which is because our treatment couch or treatment machine couch patient table is flat. So in CT simulator we also use flat tabletop. This is similar with the treatment table, and we have lasers for geometrical localization. External lasers are installed in the wall and they give us the geometric localization of the patients, and CT simulator provide anatomic informations with reference to the simulation parameters with the external lasers. Here this is a X-ray simulator, and you can see this is simply a X-ray simulator. It can be rotated 360 degree, and here is the X-ray source is here, and here is we have a detecting assembly by which we can see the treatment portals, and here is the CT simulator. Same kind of machine like CT scanner used in diagnostic radiology, but they have flat tabletop, their bore size is large to accommodate our various kinds of treatment accessories, and we have a external lasers which give us the geometric localization of the patients. And this is all for today. Thank you all.